Welcome. So if you've ever looked at a matrix on an exam and felt, a little bit intimidated, you are in exactly the right place. In this explainer, we're not just going to stare at numbers in a box. Oh no. We are going to build a powerful toolkit that's going to let you tackle some really complex problems with total confidence. All right, let's get into it. So let me ask you this. What do the incredible graphics in your favorite video game have to do with the algorithms that suggest what movie you should watch next? Or what about the methods used to encrypt super secure messages? I know, it sounds kind of random, right? But the answer is a single, really elegant mathematical concept. And trust me, by the end of this, you're going to see exactly how.
Every great toolkit starts with the basics. So before we can jump in and start solving things, we've got to unbox our components. We need to understand what a matrix actually is. Think of this as us looking at the blueprint for all of our tools.
At its heart, a matrix is incredibly simple. It's really just a grid of numbers. That's it. It's a neat, organized rectangle where every single number has its own specific spot, right? It's defined by the row it's in and the column it's in. And believe it or not, this simple little structure is what gives it all its power.
Okay, so let's break down how we talk about them. The notation might look a little complex, but it's basically just a set of coordinates. M is just the number of rows, N is the number of columns, and that little Aij is the specific number you find at row I and column J. So a 3x2 matrix, well, it's got 3 rows, 2 columns, and a grand total of 6 numbers inside. Simple as that.
And just like tools in a kit, matrices come in different shapes and sizes. You've got your row and column matrices, which, you guessed it, are exactly what they sound like. There's the null matrix, just full of zeros. But listen, pay close attention to these last two. The square matrix, where rows equal columns, and the identity matrix. This one, the identity, it basically acts like the number 1 in the matrix world, and it is absolutely crucial for the power tools we're going to talk about later.
All right, we know what matrices are. Now let's put them to work. We're going to start with the everyday tools in our kit, the basic operations that let us combine and manipulate them.
So here is the golden rule, the most important thing to remember. If you want to add or subtract two matrices, they have to be the exact same shape. A 2x3 matrix can only be added to another 2x3. You just can't add a rectangle to a square, it doesn't work. It's a non-negotiable rule, and it actually makes the whole process super easy. You just add or subtract the numbers in the same spots.
Now, multiplication is where things get a little more interesting. You can't just multiply any two matrices you find. There's what we call a compatibility check. The number of columns in the first matrix has to be the exact same as the number of rows in the second one. See how the two ends are on the inside there? If they match, you're good to go. And get this, the final matrix you get has the dimensions of the outer numbers, m rows and p columns.
And this right here, this is the single biggest trap in all of matrix algebra. With regular numbers, we all know 5 times 3 is the same as 3 times 5. But with matrices, order is absolutely critical. In almost every case, A times B is not the same as B times A. This is called being non-commutative, and I'm telling you, remembering this one little fact is going to save you a world of hurt on your exams.
Okay, we've mastered the hand tools. Now it is trying to break out the heavy machinery, the determinant and the inverse. These are the power tools that let us crack the really tough problems, like solving entire systems of equations all at once.
So what is a determinant? Well, it's a single, unique number that you can calculate from any square matrix. But it's not just any old number. Think of it more like a diagnostic key. You turn this key, and the number it spits out, that's the determinant. It tells you something really profound about the matrix, specifically whether or not it even has an inverse.
And here it is, the single most important result from that diagnostic check. If the determinant of a matrix A is not 0, we call it non-singular. This is the green light. It means the matrix has an inverse, and we can unlock all of its amazing problem-solving power. If the determinant is 0, well, it's a singular matrix, and the inverse just doesn't exist. End of story.
So what is this inverse we keep talking about? It's pretty much exactly what it sounds like. It is the undo button for a matrix. You know how dividing by 5 undoes multiplying by 5? It's the same idea. Multiplying a matrix A by its inverse, A end quote, gets you right back to the matrix version of 1, that identity matrix, I.
So how do we actually find it? It's really just a 3-step process. First, you calculate the determinant. That's our quality check. If it's not 0, we can keep going. Second,
You find something called the adjoint. Now this involves a few steps itself, but it ends with you transposing a matrix, which just means you swap its rows and columns. Finally, you just divide that adjoint you found by the determinant. That formula is your key to the inverse.
Now you're going to want to pay close attention here because this is a classic exam question. When you take the transpose or the inverse of a product of two matrices, you have to swap their order. The inverse of AB is not A inverse times B inverse. Nope, it's B inverse times A inverse. This reversal law is a super important property to have in your back pocket.
Okay, we've assembled our toolkit, we've got our power tools all charged up. Now it's time for our first big project. Let's see how all of this comes together to solve a problem you've definitely seen before, but in a way that's so much more elegant and powerful.
Everybody remembers these from algebra class, right? A system of linear equations. You probably solved them using substitution or elimination. And yeah, those methods work, but they can get really messy and slow, especially when you have more variables. Matrices, though, they give us a much cleaner way.
Watch this. We can actually transform this entire system. First, we just pull out the coefficients, the 2, 3, 4, and -1, into a matrix we'll call A. Then the variables, x and y, become a column matrix we'll call X. And finally, the constants on the other side, 7 and 3, they form a column matrix B. And just like that, our messy system becomes one sleek, clean equation, AX equals B.
So how do we solve for x? Well, this is the payoff. First, we check the determinant of A. If it's not 0, we are guaranteed to have one unique solution. And from there, all we have to do is find the inverse of A and multiply it by B. The answer, x, just pops right out. It's a reliable, repeatable blueprint for solving any system like this.
All right, you've got the core skills down. Now let's get you ready for exam day. This is the Master Builder's Guide, a rapid-fire round of pro tips and common traps to make sure you're using these tools flawlessly when you're under pressure.
These are the classic mistakes that happen when we forget that matrices aren't just regular numbers. You can multiply two non-zero matrices and actually get a zero matrix. You can't expand A plus B squared like you normally would, and you definitely can't just cancel A from both sides of an equation. Remembering these key differences is absolutely vital.
And the slide right here, this is pure gold for exam day. If you spot an idempotent matrix where A squared equals A, that's a huge time saver, because it means A to any power is still just A. And the 2x2 inverse has this fantastic shortcut. Just swap the main diagonal elements, make the other two negative, and divide the whole thing by the determinant. No need for that whole adjoint method. These are the tricks that save you precious minutes when the clock is ticking.
And finally, here's your complete decision guide. If the determinant of A isn't 0, you have one unique solution. Simple. If the determinant is 0, you've just got one more step. Check if adjoint A times B is 0. If it is, you've got infinite solutions. If it's not, there is no solution at all. This little flowchart covers every single possible outcome.
So there you have it. We've gone from the most basic definition all the way to advanced applications and pro-level exam tips. You're not just looking at a box of numbers anymore. You are holding a sophisticated set of tools. The same tools used for rotating 3D graphics, solving complex engineering problems, and even powering the algorithms of data science. The only question left is, what are you going to build with it?